I could have gone back to the original 0.9, 0.2, 0.1, 0.8 times AB equals lambda times AB, right? Could have gone back to the original equation. So I kind of did in my head, but that's not what that's not where I was. Okay. So here we have it. What's the solution? Well, what do you do here if you're not sure what to do? You write it out as simultaneous equations. Kind of remember that. Okay? So we have negative 0.1, negative 0.1a plus 0.2b equals 0, and 0.1a minus 0.2b equals 0. Well, you got two simultaneous equations and two unknowns. What are you going to do? You're going to add them, right? Or you're going to eliminate one of the variables. Well, conveniently, the first variable is eliminated if you add them. But of course, when you add them, the second variable also goes away. Why is that? Well, because when we reduced this thing in the first place, we determined that the values of lambda that make this 0 are the only ones that work. So this system for that eigenvalue had better do this. Okay? They'd better eliminate each other, otherwise this wouldn't be equivalent to this for this value of lambda. So if I made a mistake with the quadratic formula, with my factoring, or with a sign or something, it's not going to work out this way. So it's a good check. Okay? And we end up then with A equals 2B. Okay? Well, if A equals 2B, then AB equals 2BB, as opposed to 2B or not 2B. Okay? Makes sense? And B can be any number, so this is any vector where this is twice as big as this. Okay? You're going to love this in a minute. That's any vector where A is double B. Well, this is the sane diminutive situation. The sane diminutive situation, what do you know about the population vector that remains stable, that doesn't change?
Can you repeat the question?
Huh?
Can you repeat the question?
For 1,000 sane, or 1,000 people, okay, the sane diminutive vectors approach a limiting vector. What is that limiting vector? Well, you got to tie some things together, and that was a week ago. It's 666 2/3, 333 1/3. If you have twice as many sane as demented, since you have twice as many demented, twice the percentage of demented becoming sane as you have sane becoming demented, then when you have twice as many sane as demented, things ain't going to change. What's that have to do with this?
2/3 to 1/3 population.
Huh?
2/3 to 1/3 population, or
Well, that literally this literally says exactly what I just said. If you got
Yeah.
twice as many sane as demented, your vector's going to end up in the same direction. Okay? That makes sense? Okay. Well, that's for lambda equals 1. Now, this number is the number you multiply the original vector by to get the transformed vector, just the number. Well, if you start with 666 and 2/3, 333 and 1/3, and multiply it by 1, what do you get? Same thing, right? And you know that with the same demented model, the total number of people doesn't change. Okay? So this totally fits. So by doing the eigenvalue problem, finding out what the multiple of your AB vector is that gives you same direction, okay? You come to the conclusion we came to just by simple algebra. So you wonder, why did we do all this? Okay? Well, remember that what happens with these vectors is each vector moves 70% of the way toward the limiting vector, right? Or 30%. Each vector will be at a distance that's 70% of the preceding one. And you map that out, and both are really good pictures, so you've got that. Remind me to give those back to you, incidentally. Did you have a copy? Did I give you a copy when I copied them? Well, anyhow, I've got them, so I'll give them back to you here in a few minutes. Don't leave without me giving those to you. If you got to beat it out of me, go ahead. You know, I deserve it. Now, I think the two of you could handle it. Okay, if you're in shape. If you if you do that, we want to get a handle on that 70% thing. Why in the world is it 70%? Well, there's a good reason for it. But you got to see something before we can use that. So let's go ahead and find that eigenvector. And I'm going to ask you to do that. Just do what I did here with 1 and do it with 0.7. See what you get.